Welcome to this module of the ZK Whiteboard Sessions Season 3. I'm today's host, Nico, and our guest today is a former colleague of mine, actually, Ying Tong.
Hello, nice to be here.
Yeah. What's the topic for today's session?
Today we're looking at privacy-preserving constructions for digital ID, and these are going to be deployed everywhere in the US, in the EU, and we should absolutely be paying attention to them.
Can you give us a quick outline of what you have planned for today?
Yeah, so what we're going to do is start with existing constructions. So these are the constructions that are already deployed nationwide or are going to be deployed EU-wide. And these are based on a cryptographic primitive called salted hashes. Next, we're going to examine why these are broken.
Okay. It's about to start.
Yeah. And we're going to break down our privacy invariants and our privacy requirements and show why the existing constructions violate them. So in particular, we will look at the privacy invariant known as unlinkability, which prevents issuers and verifiers in the system from tracking the activities of holders. And then next we're going to fix it. So we're going to present here this sort of SNARK of a signature construction that has been proposed by projects like Google, Microsoft's Credentials, and many zkID projects in our space. And we can think of it as a privacy hardening layer on top of existing constructions that gives us back the feature of unlinkability. And then next, we're going to discuss some sort of additional requirements and properties in a digital ID system. So I think this is very much part of deploying in a real-world context. So issuers need to be able to revoke credentials. We want to preserve certain features such as deniable presentation. We want to consider extra protocol privacy leaks, like differential privacy and such. And then finally, we're going to go over the details and primitives used in these zkID constructions, and sort of the trade-offs of each one, and as well as how they interact with standards, which are important to consider when we're thinking about large-scale deployments.
Makes sense. Great. Shall we get started?
Yeah. There's many zkID projects in this space, so it's probably a familiar topic to our viewers. I think what's changed recently and why this is an urgent topic is because digital ID systems are being deployed in many jurisdictions and very, very soon. So, for example, there's like EUDI, EU Digital Identity Wallet. They plan to roll it out just next year. There's also the MDL, Mobile Driver's License. This standard is already prevalent in the United States. And a great motivating use case for many of these jurisdictions is age gating or age verification. And this is basically meant to bar access for adult content and pornography websites for persons under the age of 18. So, yeah, regardless what your opinion is about age gating or digital ID, it is happening and soon.
Yeah. So you might as well do it in a privacy-preserving way.
Yeah, I think it is our responsibility as cryptographers, as citizens, to make sure we don't sleepwalk into a surveillance state.
Yeah.
Yeah. So we can start maybe with the existing designs for these digital ID systems and also why they're broken.
Sounds good.
So this is not theoretical at all, because this design has already been deployed in Louisiana. It's called LA Wallet, and it's being used for age verification. So basically, this design makes use of a primitive called salted hashes. And how it works is you have some kind of credential, like a JSON web token or like some binary object representation. And it looks very similar to the credentials that we have for digital services. So there's a header, there's some body, and then there's an issuer who signs this token. Now, what's different about this design is that it's meant to enable selective disclosure. So
what does that mean?
Selective disclosure means that you can reveal some subset of the credential, but keep the other parts of it hidden.
Okay.
And basically, how they've proposed to achieve this is that instead of signing the plain text directly, so let's say your plain text is like some name and some value. So instead of signing this directly, they sign a hash of it. Yeah, so you get some digest.
So just to be concrete, this could be like date of birth, and this is my date of birth?
Exactly. It's all key values, like in a JSON.
Yeah.
And furthermore, to prevent brute forcing attacks, so like I could just 365 days of the year, right? They include some kind of salt.
Okay. So this is like a big random value?
Yes, exactly. This is the salted hashes design. And basically, this is encoded into, you can call this disclosure 1. Okay. Now, because the issuer has signed a bunch of these digests.
So for different key value pairs.
Exactly. Yeah, you could, when the holder present this credential to some verifier, you could choose to open only the relevant subset of values. So, yeah. And this signed credential is sort of packaged together with the plain texts disclosures, including the salts. Up to n values, and this whole thing is given to the holder. Yeah. So the verifier is only going to see the signature, the digests, and then additionally, whichever plain text the holder chooses to disclose.
Okay.
Yeah.
So you said this isn't like the best way to do it. Why not?
This is a really bad way to do this. And the reason is that these digests, along with the signature, are static. So they are random, but they are static. And
so they're always the same, no matter how many times they present my credential.
Exactly. So while it is true that I don't need to open this when presenting it, I do need to provide its digest to the verifier. And so a verifier seeing the same digest twice can identify that it is the same person who presented it. So this design, or something very close to it, has been deployed in LA Wallet in Louisiana, and people have to use it to verify their age when accessing like Pornhub or OnlyFans or maybe in the future social media.
Okay. So it achieves selective disclosure, but it fails at every other sort of privacy property we'd like to see.
I think it fails very specifically in this property called unlinkability. And yeah, this would be a very good property to discuss because it's our main motivation for moving to a zkID design. So for me, it's always useful to formally state the privacy invariant, the privacy property that we want. And how we can do this is through threat modeling. So we need to first reason about who are the actors in the system, and there's at the center of it the holder.
So the holder of the credential?
Exactly. This is the person who's sort of requesting a credential from the issuer. And the issuer you can think of as like maybe some kind of government, let's say. So the issuer is sending this document with their signature.
So like a passport, a driving license.
A passport, driving license, and it could be in the SD, it could be in the salted hashes data format. And then the issuer, this is called Credential.
Yeah.
And then the holder can present this to a verifier. So a verifier could be like, let's say a bank. So yeah. And I think one important thing to note is that at time of presentation, the holder can choose to selectively disclose some subset of this credential, and does not need to present the whole credential. Yeah. And then, so what we were saying just now about unlinkability and why it's a problem is in multiple ways. So first of all, we want there to be unobservability on the issuer side. And what this means is that given a list of the credentials they have issued, they should not be able to detect when these credentials are being presented.
Okay. So even the government doesn't know, just by looking at this, who is presenting.
Exactly. So yeah, if the issuer is colluding, even if the issuer is colluding with the verifier,
Mhm.
We don't want the issuer to be able to link any of the presentations to any of the credentials. And this becomes very important when we're considering the interactions that do happen between the issuer and verifier. So one main interaction is basically revocation. So the issuer has to be able to revoke credentials if they get stolen, if they expired, and yeah, the verifier needs some way to stay updated as the revocation list is changing. So yeah, the issuer and verifier do interact in the real world, and it is crucial that their interactions do not allow the issuer to link credentials. Another kind of unlinkability is if we consider a single verifier. So given log of presentations, they should not be able to link any two presentations to the same person, the same credential.
No matter how many presentations are made?
Exactly.
Okay.
Yeah. And then this is also true of multiple verifiers. So
multiple banks getting together.
Exactly. So even if they were to put together their logs, it shouldn't give them any extra information or allow them to correlate any presentations. Yeah. And so you can see clearly that having some kind of static hash or static signature allows linkability and observability on all these fronts.
Right. Yes. So how do we achieve these properties of unobservability and unlinkability?
The key thing we have to do is conceal the static signatures and static hashes. And operating in the real world, we're subject to certain design constraints. So we found that in particular, it's hard to change issuer behavior. So issuers are used to certain data formats and signature algorithms that have been standardized. So yeah, our design challenge here is how can we add a privacy layer without modifying the issuer behavior.
Right. So here we're saying the credential will always be like a passport. They're not going to change how they do passports, but we still have to do something on this side.
Yes,
As designer.
exactly.
Cool.
Exactly.
And maybe down here as well.
Yes, yes.
Okay.
So this set of design constraints motivated the zkID construction. And this is very much the construction that Google recently presented in their anonymous credentials from ECDSA paper. So as we discussed just now, we don't want to change the issuer behavior. And so the issuer, as before, is still going to work with SD, JET, and this contains their signature, the issuer public key, and a list of digests that are the salted hashes of the actual attributes. And then we don't want to change this.
Okay.
But we want to conceal the static hashes and the static signature.
Right.
So here at the level of the prover or holder, we can introduce modifications. And this is where we're going to introduce a zk-SNARK.
Here we go.
Yeah. So as we said, we want this SD jet to be a private input. And as we also mentioned before, we don't want to modify the data format or the signature algorithm.
Right.
So unfortunately, this means that we have to eat the cost of some SNARK unfriendly primitives. For example, ECDSA verify that takes in the signature, the issuer public key, and the message signed, which is, let's say, the digests. And then another thing we have to do is parse the data format. So we have to, let's say, parse a JSON and output, say, an array of key values.
Right. How do we jump from digests to key values?
Oh, that's true. So, the issuer, if you recall, also provides to the holder the plain text disclosures.
Okay.
And these disclosures contain the key values, as you said, as well as the salts used to produce the digests. And so, yeah, inside this circuit, we do have to open these salted digests and then parse them into their plain text.
Okay, so JSON parser will also do like some checks that these values hash correctly to the digest.
Exactly, yeah. JSON parse needs to open and hashes.
Okay.
Yeah. So no, we're not quite done yet. So I put these into one relation because if you notice, these do not change with the presentation. These are only have to do with the credential itself.
Yeah.
So regardless of which subset of these you choose to disclose, you would need to parse all of them anyway.
That makes sense.
So if you have the foresight to separate out this relations, you can absolutely pre-process them and store them.
So I do this once, and for all my presentations, I have this work already done for me.
Exactly.
Cool.
Yeah.
How do we do the presentation?
The presentation, you cannot pre-process, and you do actually have to tailor it to the verifier's disclosure request. So yeah, here the verifier is going to send you a request for a subset of these fields.
Yeah.
And in addition, is actually going to send you a nonce, a session nonce to enforce liveness.
To make sure I'm not reusing a proof from a previous session or for someone else.
Exactly. Is to make sure that the presentation is being done live by the same person to whom this credential was issued. So in this presentation relation, we have to disclose based on the verifier's request some subset of these attributes that we've parsed. And then we have to prove liveness somehow. So how this is realized in practice is that the holder's secure element is used to sign the session nonce. Yeah.
So this is trusted hardware in whatever the holder is using to prove?
Yeah, so exactly. This is one thing I elided previously, but it's an absolutely crucial element of this design, that the holder public key is also signed here by the issuer.
Okay.
And so at the time of presentation, the holder needs to prove possession of this public key and furthermore use it to sign the session notes.
Right. And that ensures that the holder is using the same device that is known to the issuer?
Exactly.
Okay.
And that the holder is in control of the device right now.
I see.
Yeah. So then these two relations have to be linked. Yeah, in the sense that they need to use the same set of digests that were signed by the issuer. And yeah, furthermore, the holder's public key has to also be consistent. So there is some linking proof as well between the prepare and show relations.
Okay.
And so all of this generates a presentation proof, which is in our case a zk proof that the verifier checks.
Okay, so this is just one proof for this, and the link?
Yes,
Okay.
exactly. So it's interesting, this design, because, for instance, the Google construction lumps all of these pretty much into one relation that's done live at presentation time.
So no prepare for them, they redo it every time?
Yes, exactly.
Okay.
Whereas there exist other designs, such as Microsoft's Crescent credentials, that make use of easily re-randomizable commitments. So in particular, they use Roth16 for prepare and can very cheaply re-randomize and link these pre-computed proofs at presentation time.
Yeah. So this looks like a super powerful pattern, right? Like verifying a signature and then parsing whatever was signed. Can we apply this anywhere? Like, is this how zk Passport works, for example?
Yeah, this architecture is generic over the underlying credential.
Okay.
So that is the power, the flexibility of generic zk proofs. So if we wanted to, we could replace this underlying data format with passports, as you said. We could replace it with national IDs. And we could even replace it with credentials that are not signed. So, for example, some kind of TLS session. For example, some kind of social graph attestation. So as long as we can input this credential into a circuit, we can use this architecture as a privacy hardening layer to realize anonymous credentials from arbitrary formats.
Right. I wanted to ask before you moved on to TLS, anything signed, does that include, like, is this also how zk email works?
zk email, yes. zk email has a DKIM signature.
So the emails are signed by someone, and then we do the same thing of proving the signature and
parsing
the
email format. Exactly.
Is it exactly the same with TLS, or are there things that change a bit?
So with TLS, the data, the session, and its transcript is not signed. Instead, it's encrypted with a symmetric key. And so we need an extra step between the session and inputting it into the proof. So, for instance, we might need to know that the prover doesn't know the whole key. Or we might need to know that the person making the proof knows the direction of the communication. And so there are various zk-TLS and MPC-TLS designs that basically allow us to make an attestation over a TLS session and then to make a proof about it. But usually, yeah, this involves introducing a layer of trust assumptions like a node array or a proxy, because the attestation has to come from somewhere.
Right. So summarizing, the problem is the data is not signed. We have this sort of symmetric encryption or symmetric MAC, I think they call it. So the prover could have issued a credential to himself, right?
Exactly.
Okay. And so we need to break that relation somehow.
Exactly.
Okay. That sounds a bit trickier.
Yes. But yeah, the very nice feature of this architecture is it doesn't change issuer behavior. And that's why this anonymous credentials from ECDSA is being considered as one of the contenders for EUDI wallet. Yeah, there's other proposals such as BBS signatures, which are lightweight and don't have the full expressivity of a generic zk-SNARK. But as a trade-off, they require the issuer to change their parsing and as well as their signature algorithm.
Right. Okay, so if we had like a super friendly data format and signature, we can actually get all this stuff for much cheaper.
Exactly.
Okay.
So I think a big challenge of working in digital ID is the need to interface with legacy standards that are widely adopted already, that people have converged around. So the big advantage of generic zk-SNARKs is this compatibility.
Right. One thing I wanted to ask is, all right, we have this architecture. Can you give us a bit of introduction as to why we get all the properties we wanted from the system?
Yeah, so as you can see, the verifier no longer has access to the static hashes or the static signature. So the verifier only sees a zero knowledge proof, and every proof looks random, indistinguishable from any other proof. I think for instance, being able to conceal as well the holder's public key is a huge benefit of this architecture. And yeah, we can see as well the issuer, just looking at these proofs, also has no idea how to link them back to the original credentials that they issued.
Right. From the zero knowledge property. Super strong. Okay.
Exactly.
You also mentioned revocation as sort of part of our threat model and something that the issuer could do. How would we do this here?
Yeah, revocation is a requirement in digital ID systems, and it's often very subtle to realize it without violating our unlinkability requirements. So there are a spectrum of solutions that have been proposed for revocation, and each comes with its trade-offs. And they're on a spectrum of linkability, basically. So the most privacy preserving revocation solution is to have the holder prove client side that they're either in a whitelist or not in a blacklist. So
I should ask before we start, here by revocation, do we mean when my passport expires, or do we mean sort of deactivating my passport before it expires?
it could mean both, yeah. But so yeah, revocation is stronger than expiry. So your passport could be revoked if you're considered a criminal by the jurisdiction, for example. Sometimes people are also interested in proving non-inclusion on a sanctions list, the OFAC sanctions list. Yeah. But expiry is also one of the methods of realizing revocation. So if each credential comes with some kind of expiry token that is only valid for a certain time window, your proof needs to include a check that this time window has not passed.
Right.
Yeah.
And so we can set this window for the token to be shorter than the window of my passport.
Exactly.
I see.
So what this also means is that the issuer needs to regularly renew this credential. And the holder needs to periodically re-register for a credential. And yeah, this introduces more interaction. And it is good to note that in the digital ID system I described, in interaction at issuance time is a requirement, because the issuer has to sign the holder's public key, if you recall. So at the time of registration, the holder actually has to prove possession of this public key.
Actually, that's something else I wanted to ask. Is that because of a legal requirement, or do we need this device binding thing for credentials in the first place?
This device binding requirement comes from, it appears in the EUDI's high-level requirements.
Okay.
But if you talk with projects like ZK Passport or projects that use physical credentials, there is not this concept of device binding, and there's no need to interact with the issuer for device binding. But for them, they are often interested in some proof of liveness at presentation time. So ZK Passport and Rarimo both are working on some kind of facial recognition client-side solution. Yeah. So this expiry tokens are one approach to revocation. And basically require more interaction between the holder and issuer. So the most privacy-preserving solution is for the client to download a revocation list and then locally prove non-inclusion in a blacklist.
Okay, so in this model, the issuer would regularly update some kind of official blacklist?
Exactly. And this puts an online requirement on the client at presentation time. So, or at least within a certain window.
I guess the verifier also needs to be aware of the blacklist.
Yes, that is true. Yeah, but as long as we're using some kind of public registry for revocation, we need to assume online communication between the issuer and the verifier, as well as the and in this case between the issuer and the prover.
Makes sense.
Yeah.
Yeah, that's the arrow you drew way back.
Yeah.
That's the initial diagram.
Exactly. So the last sort of common solution is the worst in terms of privacy. And this is basically having the verifier just ping the issuer and ask, is this credential revoked? So this violates
unlinkability, right?
Yes, exactly. It violates unobservability because the verifier, the issuer can tell that this holder is trying to present their token. And yeah, it violates unlinkability between the issuer and the verifier. So it's important to note here that this would only work if the holder reveals some personally identifying information to the verifier.
Right. So otherwise, the verifier has nothing to show to the issuer to get any kind of information. I see.
Yeah. So another interesting consideration when it comes to revocation is
to the other side
is issuer privacy. So right now, sanctions lists are public, as we know, but passport revocation lists are not public. So they're available to law enforcement officials and the borders, for example. And a concern with public revocation lists might be that the issuer doesn't want to reveal sensitive information. So, for example, if you're a business and you're firing employees and revoking their employee passes, this might reveal some information about the state of your business. So I wanted to bring this up as an interesting privacy invariant that doesn't get considered as much as holder privacy.
Right.
Yeah.
Are there other sort of additional features or additional privacy properties that we should be considering?
Yeah. Another one that comes to mind is deniable presentation. This is also known as plausible deniability or repudiation. So this is a feature that the holder, after presenting a credential, can plausibly deny having presented it. And this is...
No, I did not go to that adult website. It wasn't...
Exactly. I think of them in the context of physical interactions especially. And in fact, in the UK and in the US, many of these digital ID systems are partnering with physical venues like clubs, pubs, liquor stores. And the idea is they would replace the presenting your physical license. So yeah, the worry there is that this digital interaction will somehow produce a trace. And
even though we have unlinkability?
If we have full unlinkability and it's a fully offline presentation, I think that's good. But yeah, when we're considering, let's say, the wallet provider or metadata, other ways to fingerprint an interaction, that might create a trace. But
so like my network address or the timings at which I present credentials maybe, or...
Yeah. All the things that could be used to fingerprint you in a digital interaction that you couldn't in a physical interaction. But for our purposes, we are worried about sort of linkability when it comes to pseudonyms. So it is a feature in many digital ID systems that we want to have a long-lived pseudonym between the holder and verifier. So even if the holder conceals her actual identity, maybe they want to access repeated services, accumulate points, with a service provider.
Right.
And in those cases, a long-lived pseudonym is a useful feature. Now, this enables linkability in the single verifier case.
Okay.
Right. And basically, as long as a single verifier is able to link your presentations, they will be able to then show it to a third party. And even though each presentation is selective disclosure, we have to consider the combination of credentials, of presentations, and whether or not in combination they might be personally identifying.
I see.
So, for example, there was this study that found that just the zip code, birthday, and sex of an American was sufficient to uniquely identify 87.1% of them. So if for a single verifier across multiple presentations with the consistent pseudonym, the holder reveals some kind of personally identifying subset of attributes, this could allow the verifier to identify them and prove statements about them to a third party.
Right.
Yeah. And in this case, deniable authentication becomes interesting, or deniable presentation. So even if the holder has revealed personally identifying subset of attributes, we want them to be able to deny having had these interactions. So the one very simple construction of this is
sorry, before we get to the construction, to make sure I understand, we want to be able to say, so the verifier will claim, I have seen someone show up with this zip code, this birthday, and this gender. And myself, if I'm the targeted person, I want to be able to say, no, the verifier is lying. I've never been authenticating with them.
Exactly. Okay. You want to be able to accuse the verifier of forging these proofs.
I see. Okay.
Yeah. And one way you could do this is we had our relation just now.
Our pair and show.
Yeah, relation, like we had prepare, show. So yeah, taken on its own, this relation, like a proof of this relation, is very hard to deny because you're proving possession, in particular, of a certain public key that was signed by the issuer. So how we can bootstrap deniability is we can add another pathway for verification, which checks whether or not the person making the proof is the verifier.
Right.
So if the verifier wanted to forge a valid proof without knowing any of your attributes, without possessing your phone's public key, it could simply input its own private key and fulfill like this branch of the relation.
I see. So myself as an honest user, I'll use this part, and this will always be false. And the verifier, well, someone observing a proof coming out of this doesn't know which path was taken.
Exactly.
Okay. So it could be either an honest user or just the verifier.
Exactly.
Wow. Okay.
So I rarely see this property being discussed in digital ID constructions. And I think there's a lot to explore here. For example, making it very easy for verifier software to forge proofs that would strengthen the claim. And also perhaps allowing anyone to forge a proof after a certain time window. So that, again, the set of people who could have forged it is like large and your claim is more believable. Yeah.
One additional question, how can we avoid these kinds of situations? Because this seems very inconspicuous, right? Like, I'll give you a zero-knowledge proof of my zip code, birthday, and sex. Like, what's the worst that could happen?
That's a really good question. And there are many ways to de-anonymize a holder outside of the protocol. And one of my worries for zkID, or privacy-preserving IDs, is that it sort of lulls us into a false sense of security and encourages us to reveal, paradoxically, more than we would have otherwise.
Right.
So I think there's been a lot of studies when it comes to differential privacy as well, of how the relationships between attributes can actually be personally identifying. So yeah, in some sense, it's orthogonal to the cryptographic design, the protocol design. But yeah, I think it's important to keep in mind, and it's important not to fall into the trap of thinking that just because something is zk or selective disclosure, that we can let our guard down. And yeah, in fact, placing restrictions on what verifiers are allowed to ask for, I think is a good starting point.
I guess, for example, with let's say I'm doing a job interview and the verifier is asking me my sex, I would love to be able to say to them, like, please no.
Right.
And all information you need to know, right?
Yeah. There's definitely, when it comes to selective disclosure, a spectrum of use cases. There's some use cases where the verifier does need to know everything about you. So
I guess something medical, for example.
Exactly. And in that case, you don't need selective disclosure at all. So really, this only matters when the verifier is only entitled to some subset of the attributes. Yeah. So yeah, these privacy invariants like unlinkability, unobservability, deniable presentation, they interact with these extra protocol attack vectors. Yeah, and I think the idea here is that if we have a system that is very limited in what it can do and what it can learn, then we guard ourselves from these attacks or make them easier to reason about.
So far we've been sort of looking at the construction from quite a high level, and we've been saying like ZKP is this black box. I was wondering, we have a whole zoo of like zero knowledge proofs. I was wondering if there's any proofs that we prefer using over others, any properties that are super important.
We've seen a range of designs already. I think maybe a good illustration, a comparative illustration, is Google's design versus Microsoft's. And the Microsoft design is called Crescent Credentials. So, as we recall from previously, we have two relations, prepare and show.
And the link, right? But I guess.
And the linking proof, enforcing consistency of the inputs shared between them. So in Microsoft Crescent Credentials, these are two different phases, and they use Groth 16 for the prepare phase. So now, the benefits of this is it's very efficiently re-randomizable. And
so this is a property of Groth16 proofs, that they're easy to...
Exactly. They're easy to re-randomize, and
so that means I can make a new proof without having to like recompute everything from scratch. Okay.
exactly. And yeah, it's a good point here that you cannot literally just reuse the same proof, because then that's a static proof and it's linkable. Right. So, but as we know, Groth16 needs a trusted setup.
Yep.
And this is true, for KZG, any system that uses KZG commitments as well. And in fact, Groth16 also needs a per circuit trusted setup on top of that.
Yeah.
So, yeah, in many ways, this is an anti-feature, because you are coordinating across a huge ecosystem of issuers, verifiers, who don't trust each other necessarily, and would want stronger guarantees than a trusted setup. So how do we make sure that they're somehow all contributing to the trusted setup? That's a coordination problem.
And what if the circuit needs to change for some reason?
Yes, exactly. But one way to think about the trusted setup is it could actually we could make use of our existing trust assumptions about the issuer to instantiate a trusted setup. So this could actually be a feature. So what I mean is, right now, the issuer can already forge whatever credentials it wants to.
Right. Yeah, the government can make new passports.
Yes.
I mean, we hope there's some kind of watchdog, but
Yeah.
anyway, for the sake of argument, issuers can forge.
Exactly. So if the credential is signed by the issuer, this means the issuer holds the private key and can sign whatever they want. So if we give the toxic waste from the trusted setup to the issuer, have we really changed anything about the trust model? So the issuer,
with the toxic waste, can produce any proof they want.
Yes, it can forge proofs of invalid for not unsatisfying witnesses. But basically nothing has changed.
Right. They could already forge presentations by forging a credential.
Exactly.
Or forge presentation just by forging a proof.
Exactly.
I see.
Yeah. So yeah, I think designing in real world contexts, very often the constraints and the trust models actually expand your design space. And carefully examining who we already trust can help us make decisions about downstream tech stack. Yeah, but basically we can instantiate a designated verifier Groth16, allowing the issuer to forge proofs.
Right.
Yeah. So whereas in the Google case, they're using some combination of GKR and Liheru, that is zk. And so this is not efficient to re-randomize. So so it uses the BCS transform, which commits to the witness using Merkle commitments. And so unlike the Groth16 commitments, these are not homomorphic. And if we subsequently want to re-randomize them, we basically need to redo the whole proof.
Right.
Yeah. But because they don't use, they don't need a cryptographic group, they don't use discrete log, they don't use pairings, they can use very small fields. And actually, they can use arbitrary fields. And so I think you'll hear in the ZK podcast episode with them that they exploited this property to the fullest and chose native fields and binary fields and basically just the most efficient fields for the underlying operations.
Right.
Yeah.
So they make up for the fact that they have to redo prepare, but just making sure that everything is super fast and you can do all this quickly, right?
Exactly. So even though they have to each time recompute the whole relation, they've made it just I think it's about on the order of 1 second or 2 seconds on a phone. Yeah. So I will say that a setting that might be interesting to consider is multi-credential presentations.
What does that mean?
So instead of only presenting a single credential, you're taking multiple credentials and linking them somehow.
Right.
Yeah.
So my passport, my driver's license, maybe some email I had.
Some email, your bank statement. Yeah. And then when it comes to multi-credential presentation, it can get unwieldy quickly if we don't have an efficient way to pre-compute them and to link them.
Right.
So yeah, basically in the case of like say n credentials, the Google relation possibly would just blow up to n times its size. Whereas for Microsoft Crescent credentials, we don't pay at all for the pre-processed proofs. And then so the factor of n is like only at the show, which is way smaller.
Right. Makes sense. So it seems that even though it's like one general architecture, there's still many approaches to do things. Question I have is, if we want this to be like actual legally binding ID, do we need some kind of standard way of doing this?
Yeah, a lot of these solutions are targeting national level ID systems. So like the EU digital ID wallet, as well as the mobile driver's license in the US. And so it becomes crucial to be able to specify and standardize your scheme and provide assurances about security. So another good thing about Google's design is they only use standardized cryptography. So yeah, they only make hash functions basically.
Right.
And yeah.
Whereas the stuff here is less standard, more recent.
Yes, they in particular need pairings. And that has not been standardized by any major standards body. So a big part of a digital ID project that interfaces with national level stakeholders is to be able to work with standards bodies like the IETF and W3C and ISO. So yeah, For example, Google has their libzk informational draft on IETF, and I have been working on the standard for polynomial commitments here. And yeah, in many ways, privacy-preserving digital ID is the zk community's first contact with standards bodies. And the W3C is a kind of a higher level standards body that they take primitives from the IETF and use them in applications or and web level.
So IETF likely to standardize the specific zk proof for use, whereas W3C, the whole like, here is how I construct a presentation.
Exactly. The W3C wants to be able to consider the zk proof as a black box. And then use it in higher level applications like verifiable credentials and data integrity proofs. So yeah, besides these standards bodies, yeah, there are many others. And yeah, I think the benefit of standardizing something is it's provides a security guarantee. So if your implementation conforms to the standard, then it's going to be that, let's say 128-bit level security is guaranteed. So yeah, I encourage people working on zkID or privacy-preserving digital ID to get familiar with existing standards and start to think about how we can work with these standards bodies or even start to standardize our own schemes.
Makes sense. Thanks. I think that's a good place to wrap up. Let's see if I can summarize sort of what we saw. We had first the strawman protocol of how to do selective disclosure, and we saw that doesn't work because our credentials were static and our presentation was static as well. Then we looked at the threat model. We realized our presentation needs to be randomized somehow or private. We have this SNARK of a signature system that you showed. Then we discussed extra properties like deniable presentation, the worries about de-anonymization, and then specifics of what proofs can we use and how do we standardize them. Amazing. Thank you very much.
Thank you.